Dr. Kutlu Demir Kandemir is a senior engineer serving as chief unit leader at Aselsan with extensive experience in the defense industry across roles as mechanical engineer, team leader, system architect, and project manager. He has led multidisciplinary teams in the development of advanced defense, robotic, mechatronic systems, combining expertise in system integration, real-time control, and product-oriented design. His professional focus includes stabilized IIR seeker systems, Robotic Systems Engineering, optomechanical design, development of scalable architectures for robotic platforms. With a background in mechanical and control engineering, Dr. Kandemir's work spans robotic locomotion, real-time embedded systems, and system engineering. He is also currently given a controls course. Basically, it's an EE course offered to the industry engineer.
Çok teşekkür ederim Mert Hocam, sağ olun. So, good afternoon everyone. It's a pleasure and privilege for me to be here in ROMER Talks. And today I will not just tell you a story about robotics, but a story about collaboration, learning, and an award-winning project which we built as a new product line in Aselsan. So this is the brief outline of my presentation. So let's start again with an introduction. I have completed all of my degrees in mechanical engineering department in METÜ, and I have experience more than 80 years in the defense sector. In the first 11 years, I worked as a missile and IR system seeker designer in TÜBİTAK SAGE, and then for the last 7 years, I'm working in Aselsan, mostly as a servo and as a system designer. Currently, I'm holding a systems engineering team lead position in Aselsan SSD sector. And in the meantime, I'm part-time lecturing on courses in systems and control. Last year, it was in TEDU Mechanical Engineering Department, and this year, it's in this EE department, EE 381, to focus to industrial engineers. And my specialization spans in robotics, real-time systems, mechatronic system design, control design, real-time embedded systems, electro-optical system design, the missile IR seekers, and to some extent missile guidance. So there is a Turkish saying that goes, you shouldn't speak ill of the dead. Ölünün arkasından konuşulmaz. However, today we are going to make a small exception just for academic purposes. Today I will talk about an award-winning collaboration project that we have done together with METÜ ROMER academics. And I don't want to talk about what has ended, but I want to talk about what we have built, what we have learned, and what remains afterwards. So, the task 3 years ago or 4 years ago, the task was clear. Our requiring entities asked us to develop a quadrupedal robotic platform for field applications. In order to control a land, you must put your boots on the ground. This is a military saying, and it's correct. But this is a dull, dirty, and dangerous task. So, and which this is totally can be achieved by robots. This is the intention. And you don't want to send your military personnel to a dangerous location. You want to do most of the dangerous task with a robot. That was their motivation. So the primary objectives were designing a locomotion system which is stable, which is controllable, and which has a modular architecture. And this should have a realistic operation requirements. But just after just after we started working, we realized that this is a state-of-the-art development effort. This is far beyond the traditional product development cycle. You need to have a academic backbone and continuous research support to satisfy these requirements. This is not just a plain design and sell type of task. So that's why we connected with ROMER to build a structure where Aselsan's engineering capacity and ROMER's academic depth could work side by side. That was our beginning point. So our mindset was product-oriented from the day one. We had to deliver a usable, field-ready system, and which was engineered for operability, not for just experimentation. So the TRL definitions were our guideline from the beginning. We were trying to develop a system which is TRL 7 or 8. I emphasize this point a lot to my newly started colleagues. So the concept of technical readiness, designing a product is very important. Producing something which works most of the time is not enough. When you are working in industry, you should be answering lots of questions, doing lots of extra work to come up with a product. And in this project, our aim was always coming with a usable product. And the quadrupedal robotics was a new territory. We should define the concept of operations with requiring authority. This was an essential task. And by the requiring authority, we mean such type of movements. This is a realistic operation case. So when we give a robot to a military personnel, they tend to behave like this. This is not a wrong thing, actually. They are working in the field. They are working in very harsh conditions. And the thing that you supply to them should be robust enough to withstand such loads. And after, together with this concepts of operation design task, we implemented a continuous dialogue with end users. And we tried to refine and filter operational requirements. And we wanted to transform them into realistic design parameters. Actually, this is also an important issue. Because when you're talking with a customer, getting all the data, as they say, is not a good thing. Because most of the time they don't know what they want, and sometimes they don't explicitly say what they want, what they need. So you need to understand them, you need to understand their problem, and you need to come up with a solution which will fit well. Actually, this iterative approach resembles a startup's MVP cycle. You should build, test, validate, and evolve. This is an iterative process. Technically, we were like a startup team within Aselsan working on a new field of engineering. And this stage marked Aselsan's hands-on response to the challenge, developing a robust engineering culture that bridges research with real-world applications. This is something which Aselsan is very proficient on. So I will continue. This is how our design cycle evolved. First, we started with a single leg, then 2 legs. After that, we managed some tethered walking tasks. And before the project was closed, we were able to walk in different terrain conditions in the blindfold form efficiently. So this was, again, an evolved design sequence. So the next part is, I think, the most important outcome of this study is the concept of robotic system engineering. So when we attacked this problem, we were aware of the fact that robot locomotion is only one problem. So the rest is system design. If you are after a TRL 8 or 7, 8 level system, you should design a total solution. You cannot just focus on locomotion software, but you have to focus on the total problem. And this requires a solid systems engineering framework. You need to make trade-off analysis under SWAP-C constraints. And you should integrate different disciplines together within the scope of the robot limitations. And within Aselsan, We developed a robotic system engineering sense in a multidisciplinary fashion. So luckily, we have image processing teams, power distribution, power design teams, mechanical design teams, communication hardware experts we have. Also, we have specific servo teams that design payloads and payload control interfaces. And also, we have specific UX, UI design, industrial design teams. So while dealing with locomotion, you should also deal with those teams, combine them together, and enforce them to fit in a volume which is 1.5 meter size and which can carry only 10 or 12 kilograms. Normally in Aselsan, we design systems on which we can go, jump, and walk. Okay, those systems can carry several tons of weight, but our robots cannot do that. It should be small, it should be power efficient, and our most important task was forcing every other design team to fit in that envelope. The SWAP-C goals were the most important goals that we sought for during this analysis. And actually, this process was powered by a complete shift in mindset, and we had to move away from our comfort zones. Actually, from comfort zone, I mean, it can be a proprietary, big closed workflows like MATLAB or MathWorks solution sets. We had relied on those type of expensive solutions to get a reliable and fast solution in our other type of systems. But in robotics, since it's a evolving and new area, you cannot rely on a proprietary software. It was a hard task for us, but we managed to do it. We developed a seamless real-to-sim and sim-to-real bridges. What we see on the simulation most of the time would be what we see in real world. The simulated software could always exactly exported and embedded in a hardware. We forced ourselves to work in that fashion. This was important. We used Mujoko integration for physics simulation, and also a real-time balance and torque-based control is implemented with my team members. So our first prototypes were called Demir 100 series, which were built on COTS state-of-the-art robotic platforms, the ones you see above. Starting from this high standard allowed us to set a clear benchmark to ourselves. We had to reach or exceed that level of performance and reliability in our Demir 200 robots, which is the one on the bottom, as you see in the previous video. We set the bar very high. We put a high standard to ourselves, and we forced ourselves to reach that standard in the long run. And so we started with integrating external systems, external robotic systems. So integration is also an important robotic skill. Next, we created our original ones by looking at the good examples. So we shifted from being a product user to a technology developer. So this stage represents a real turning point of the journey. What we ultimately built wasn't just a robot, it was a new way of engineering. I can say this new way of engineering because systems engineering is a very wide, has a very wide range. You can consider an space mission, an air-to-air missile, and an air defense system, or a car as a system engineering task. Okay, system engineering has a very broad scope. However, when you switch to a robotic system design, it has its own complications. As I said before, SWAP-C becomes your major concern. The serial production requirements also become a concern because you cannot always rely on a very expensive, high-power computational board. You must be able to do your real-time or non-real-time tasks with the readily available computer, which can be purchased in the long run, so and so forth. So those requirements forced, actually, we learned all of those requirements by doing ourselves. So it was a very experience-driven discipline formation. From control logic to system level design, we believe that we have applied a good example of robotic systems engineering. A sustainable capability comes from engineers who can bridge disciplines and make complex systems work. Actually, this is an important point to note, because I think collecting some sort of capabilities would not be enough in the near future. Actually, after the AI boom, we can also see that. Being able to program in C++, in Python, or being accustomed to some standard chipset will never be enough afterwards. You should be fluent in those tasks. You should be able to implement them together, communicate with other design teams, and make things work at the very end. This is the important task, and you should be after it. So in that sense, the hardest and the most important skill is being a robotic system engineer, being able to learn the field, learn the new upcoming technologies, and being able to integrate them to serve to a purpose. So the next part is actually giving some details about what we achieved with ROMER, because all of the things that I have explained so far were conducted with Aselsan and ROMER collaboration. So this concept, actually ROMER's role was idealized by Professor Dr. Erol Şahin. In a meeting, I think it was in 2022, he proposed the idea, he proposed his vision about how an academy-industry collaboration should be. He underlined that the academy should not be considered as a subcontractor, but as a co-developer. So actually, this idea resonated on me and on Dr. Mert Ankaralı, and together we have formulated this collaboration. And this collaboration, after it's put forward, it realized by primarily with those professors, and Dr. Uluç Saranlı, Dr. Afşar Saranlı, Dr. Ali Emre Turgut, and of course Dr. Mert Ankaralı. They were our academic mentors and technical feedback giving authorities. We conducted a co-development of algorithms and architecture together with them. So, so what I mean in co-development is resembled in these pictures. We actually conducted really hands-on experiments together with them. They were in our facility in bi-weekly or weekly meetings. They were directly inside our design scheme. They were giving us feedbacks. They were explaining how our software architecture should be. They were seeing how our robot behaves, and they were giving us feedbacks. And actually, this is something that you cannot procure. You cannot find a set of robotic professors, and you cannot convince them to come into your facility and teach you something. In this manner, I find this collaboration very unique and hard to find one. This was a very brilliant thing for me to do. We also had some collaboration with ROMER facilities too. ROMER has very nice laboratories. They have some motion capture systems. We have brought some of our robots to there and took some test data to improve the robot's locomotion algorithm. And also, as a part of this collaboration, some of my colleagues were conducting their graduate studies. they started to give some academic outputs. Here is a conference from, I think it was in Italy, and hopefully the next academic outputs are in the way. We are expecting our friends to continue this journey. So this academic collaboration with ROMER was actually conducted in twofold. So there are theses, there are publications and annual seminars, and it's a shared ownership of knowledge. And one side, there is we call it academic collaboration. In academic collaboration, our professors supported the graduate studies of Aselsan engineers through their academic guidance in the subjects directly tied with leg locomotion, perception, and related fields. And this helped a continuous knowledge generation and intellectual depth to be implemented both in our company and in our colleagues. And in the other side, the task was design support. And design support is depicted in the previous slide. As you saw, our professors directly came to our lab with recurring timely meetings. They have helped us to conduct literature review. We were doing hands-on experimentation. We conducted short technical courses. Actually, since I'm a mechanical engineer, the Kalman filtering or this whole stochastic process design is not, I'm not so efficient on that side. Dr. Afşar Saranlı conducted a short course, and from a stochastic point of view, he gave the Kalman formula, Kalman filter formula to us. It was a very enlightening moment for me. We had some very nice, very good short courses too, which were fundamental in robotic theory. Also, they gave us direct feedback about academia and industry. So in this way, this improved our development cycle. So together, these two branches formed a sustainable bridge. So this turned the academic knowledge into an industrial capability. And this is exactly how an academic and industry partnership should be, in my belief too. So I mentioned about some seminars. We were planning to do at least 3 seminars. We managed to do 2 of them. And I'm going to share some captures from those seminars to give an insight on what we do, what we were talking about. So here you can see a section from Dr. Ankaralı's presentation. And Haktan gave us a seminar about how visual inertial navigation could be used in robotics in GPS-denied environments. Dr. Afşar Saranlı have shared some of his publications and his ideas about estimation and fusion techniques in robotics. And also my friends have explained how they designed the robot locomotion software in some of their presentations. We have implemented some rule sets for leg locomotion, for balancing and gate scheduling. Those were direct outcomes of these seminars. So these seminars actually were the foundation of their thesis and their upcoming academic outputs. And we were actually directly involving the locomotion problem. We didn't use any kind of closed software algorithm. Beginning from system state machine to the generated torque values, all the pipeline, all the algorithms were designed by my team members. We were conducting the real time, the non-real time, the time logging, the display, every part of the problem. We were touching every part of the problem, and that's how we created a cumulative design methodology. So the last and the most funny part, the outcome. So I think the most important outcome of this study was the hierarchical control stack, which starts from gate planning, having the whole body control and the actuator control. This is the core of robotic control system, and you can use this methodology either quadruped, in a biped, or even in a robotic arm. This is how things work in the robotic field, at least for the time being, and having a knowledge in that sense is the crucial part, is the biggest win in terms of technical side for me. We also learned how to collect data, how to design an experiment while the design itself is going on. So the unit test philosophy is very. We have the very basic understanding on conducting unit tests in our algorithm designs, and especially Dr. Uluçsaranlı had a lot of contributions on that to make us understand how it is important. And also we created a very nice simulation and hardware interface. As I said before, the code that runs on the robot is exactly running in the simulation. With just toggling a switch, we were exporting the code to the robot or to the Mujako simulation. And actually, this is the topology of our control scheme. First, at the top level, you speak with the outside world. You get the commands, and you get the velocity commands from the user, and also you estimate your robot's position and other related states. And in the middle part, in our case, we were using MPC-based control. You schedule your steps, and you implement an MPC to adapt for the sensed ground reaction forces. And in the core, at the highest frequency, you apply a whole body control, and also at the outputs of this whole body control is directly fed to the robot actuators, the leg actuators. This is a layered hierarchical control architecture, and we have successfully implemented this. So in the end, we had a scalable, modular locomotion architecture. This can be considered as the systems overview. So there is a low-level control PC, which runs the real-time tasks, and there is a high-level PC, which runs mostly on ROS2, and conducts the tasks that are related to the robot's end purpose, sensing, planning, manipulation, so and so forth. And there is also a remote control unit. This also should be compatible with the rest of the design. And also the user experience is the most critical part here. We have, as I said before, we put a lot of effort on to make sure that the user controller, the interface is easy to use. So at the beginning, our robot started walking on a band. So after that phase, we managed to in a blindfolded fashion, we managed to come up and down through stairs. Actually, this is a very hard to do task, at least for a team which is starting from scratch. Right now, I'm expecting my friends to write another paper specifically on this blindfolded stair climbing algorithm. And also, again, another tedious task. in a unstructured terrain, when there is a very large gap, you should be proficient in going down or up that gap. Right now, the robot does not see outside world. It senses it through its legs, and it walks in a blindfold fashion. Doing this in the blindfold fashion is the first step that you should conquer. After that, you improve your system's design with vision mode. This was actually our plan. We couldn't manage to conduct the vision mode side, but at least for blindfold walking, we were, I think we were at a quite nice place. So our plan was actually providing some systems with state-of-the-art, high-quality robots, learn how to design robotic systems with those type of products, which were actually expensive but high-quality products. And in the long run, our intent was to replace all of them with a native, our own robot. That was our intent. And for me, I can say that up to the date that our project was ended, we were we were fitting in our schedule. Everything was going nice, and I think rather than being able to realize it or not, I think the most important thing is to show both the military, show the other counterparts in defense industry. We managed to show that this is an achievable, and this is a realistic, and this is a high quality task. We managed to do this, and at least brought this concept to a certain level. So this is a video that we have planned to show this year, but we couldn't do it. So you are the lucky ones to see it. This is a brief overview on our Demir product line. So there are some military-oriented payloads, but you can see, again, you can see Demir 200, the native robot properties too. So we have implemented some military payloads, and also we made use of Aselsan's readily available features, some things like stabilized tracking systems, image tracking systems. Also, our native robot was able to walk in unstructured terrain quite well. So, to sum up, I think the projects end, systems evolve, but the knowledge stays. And that's the bottom line of my presentation. That was the important thing for me. That's the catchphrase of all of these study. So I think another very important thing about what remains after the end is the nice memories. So before ending my presentation, I want to specifically thank to my friends Hasan Can Özden, Ömer Tarık Banuş, Emre Tanfener, Hasan Öftun Orhon, Mehmet Şahin, and Başak Sert Boşnak. They were my team members throughout the study. I managed to do all of those tasks with their contribution. They stick to the plan. They behaved as we expected, and also they flourished this field with their added value. They were always beyond what we have asked, what I have asked from them. I specifically want to thank my team members. And those were nice captures from our work, from the lab, or from the several items that we managed to deliver to the customer. And finally, we managed to do some nice fail videos. I think it's the most cool part of a robotic design task. Most of the time, being able to have a fail video is quite nice thing. So this dude probably knew what was coming, but we couldn't read. Our bad. Anyway, so thank you very much for your attention and your time. If you have any questions, I'll be pleased to answer it.
Why do you postpone the visual integration into the product?
Actually, that's a really nice question. This is again related to a product design lifecycle. The concept of MVP actually dictates this. First, you should produce a minimal set of requirements. You should satisfy them, and incrementally you should improve it. So consider the case when you just have a metallic body with 3 DOF legs, 4 times 3, 12 motors, and you want to come up with an end product which has vision, both blindfolded and vision modes. So the first thing that you should achieve is a blindfolded motion, because capturing the image, planning, conducting all the gate schedule with respect to that image is another non-real time and tedious task. Before doing it, you should get the low-hanging fruit. Actually, this low-hanging fruit is something Uluç Saranlı uses most of the time. First, we had to come up with specific low requirement set. We should accomplish it. Then we had to implement vision mode. Actually, the modularity that we were after from the beginning of the project would enable that task if we managed to finalize it. So our software architecture, so my friends are here, he can also comment on that. It would allow us to implement any kind of data that would come from an image processing algorithm. And that image processing algorithm would create a local near field map, and on this near field map I was planning to quantify the locations which I could easily step over, and if I could have fed that data to my locomotion algorithm, then everything would be clean. So this comes from the necessity of minimum viable product philosophy. First you should take the low-hanging fruit, then you should aim for the higher ones. If you aim for the higher one from T0, then you won't be able to show something to audience, to the customers. Okay?
Kabaca öğretecek olursam, genel olarak neden hazır platform üzerinden gidildiği, burada farklı olarak neler yapıldı?
Tam Türkçe yapalım isterseniz. Hazır platformlarla gitmemizin sebebini kısmen açıkladım. Belirli bir ihtiyaç vardı. TSK'nın bu noktada hani bütün bu geliştirme sürecini bekleyecek bir vakit yoktu esasında. Zaten bir noktada siz en son ürünü geliştirmeyi hedefleyerek diğer tüm süreçleri beklettiğiniz zaman günün sonunda bu proje yaklaşımı da hata yapmaya çok mahkum. Sonuçta elde kaliteli, satılabilir, tedarik edilebilir hazır bir ürün var. Ben bu ürünü alıp bunun üzerine faydalı yük tasarlayarak öncelikle acil ihtiyacı giderip ve harekat konseptini belirleyip bir çerçeve çizebilirim kendime. Çünkü müşterimiz de robotla nasıl çalışacağını, nasıl kullanacağını henüz bilmiyor. Bacaklı robotlar sahalarda yaygınlaşmadı. Yani evlere bile işte robot süpürgeler girebildi. Daha fazla ötesine gidilemedi. İnsanların bir yandan robotla haşır neşir olmayı, onu kullanmayı, sivil ya da askeri bir amaçla kullanmayı öğrenmesi lazım. Buradan edinilecek dersler ayrı. Kendi başına işin çekirdek teknolojisi olan locomotion software'i yapmak, bipedal ya da quadrupedal locomotion'ı yapmak, robotik yazılımını geliştirmek ayrı. Biz ilk baştan hayır efendim biz kendi robotumuzu yapacağız, onun üzerine kendi payload'umuzu takacağız deseydik ben bugün size muhtemelen bunların hiçbirini gösteremiyor olacaktım. Ben şu anda ihtiyaç makamına daha yeni bu hafta başı itibariyle bir tane hazır platform entegre sivil amaçlı kullanılacak bir ürün teslim edebildim. Ama onları verirken de yanında sürekli şeyi gösterdim. Bakın şu anda size yüksek fiyatlı bu ürünü veriyorum ama benim planımda bunun daha hesaplı, yerli olan, tedarik sorunu yaşamayacağınız bir özgün versiyonunu da hazırlıyorum. Benim yaklaşımım bu, benim çizdiğim çerçeve bu. Siz sadece bir robot almıyorsunuz, bu felsefeyi alıyorsunuz. Ben müşteriye böyle yaklaştım. Aslında bu sorunun da cevabı bir önceki arkadaşımızın sorusunun cevabını verdiğim gibi product design ile ilgili. Yani ürün geliştiriyoruz, bir çözüm geliştiriyoruz. Sadece spesifik bir işi yapan bir robot yapmıyoruz. Burada bir genel felsefe var. Böyle özetleyebilirim. Bu arada şey de söyleyeyim, hani bu bahsettiğim lokomasyon yazılımını direkt kodlayan arkadaşlarımız da burada. Teknik bir konu varsa hani sorabilirsiniz. Direkt kodlayan arkadaşlardan da yanıtını alabiliriz. Evet. Çok teşekkürler. Sağ olun vakit ayırdığınız için.